Good afternoon, everyone. Welcome to this session on recommendation systems for wide transactions. Before we get started, just a show of hands, how many of you work on recommendation systems, know about recommendation systems? Okay, good. Not many of you, so perfect audience. So about me, I am a principal data scientist at Red Hat. I work in Bangalore, India. I have a background in statistics, and I used to work for investment banks, movie studios, and high-tech companies before I joined Red Hat earlier this year. I'll be talking about the project that I work on and some of the challenges that we faced in the next 20 minutes. The rough agenda of what we would do in the next 20 minutes would be something like a very quick primer on what recommendation systems themselves are, and talk about the specific problem that my team and I are working on, and see what kind of challenges we faced when we went with textbook scenarios. And I'll talk a bit about how we overcome the challenges and eventually how it's deployed in production right now. Any of you every one of you have used internet, and recommendation systems are ubiquitous in the internet. So if you go to Amazon, you would be able to see, when you search for a product, recommendations on people who are like you would have bought something. It makes some recommendations. Or it could just be something like you go to one of these retail stores, and based on the transaction purchases that you have, they develop mining algorithms to run on top of it to get some of the recommendations. Just a minute on the basic terminologies that are used in recommendation systems. We have something called the user item matrix that you see on the right. So for every user, that's the item. 0 here represents that they haven't bought. Absence doesn't mean they're not interested. We just don't know that, and that's where we need to recommend if they would be interested in that or not. The numbers themselves mean that they have bought something. It's the weight of it. One way to think about, so this is where explicit versus implicit feedback comes in. If you've seen movies on Netflix, then at the end of the movie you can rate with the number of stars. That's changed now, but you were able to rate the number of stars until last month, and that's an example of explicit feedback. You tell how much weight you're giving to that particular movie. Implicit is something where you don't have an explicit weightage assigned. You just know if they clicked a website or not, and so that's just implied. Basically, you can do 3 kinds of recommendations. One is user-user. So you can recommend users who are similar to you. This is like what matchmaking sites do. So they tell, this is a person that you would be interested in or similar to you. The other is an user item, like the example we saw in the previous page with Amazon, where people who are similar to you also bought this item. That's an user item recommendation. The third is an item recommendation. So people who bought this item also bought this item. An example is people who bought the new Mac also buy the HDMI cable, because you have to buy all the cables with it. So that's an example of item. This is the class of models we'll be talking about today. It's called frequent patterns, where given transactions, you want to identify frequent patterns, transactions, items that came together, items or products that came along together. It has a lot of interesting applications. You could figure out, for example, in a brick and mortar retail store, you want to figure out how to place 2 categories together. That's an example of that came from market basket analysis, a famous study which tells that people who bought beer also bought diapers, right? So that's an example of that came from market basket analysis. It also handles cold start situations where you don't have much information about the user, and you cannot really personalize. All you have information is about the products that you sell on your platform or the services that you provide. The other thing is retrieval, where you can use frequent patterns and do interesting stuff on top of it. So this serves as an intermediary layer. Two things that I'm interested in for my product are cold start situation and retrieval. I'll cover how we do retrieval, the last slide for today. The common algorithms, it all started with a priori algorithm that doesn't really scale, so don't even think about it. The most common methodology of obtaining frequent patterns is this algorithm called FP growth. Spark does a brilliant job of FP growth. They implement a parallel FP growth version, and that's like the most commonly used frequent pattern model right now. It creates FP frequent pattern trees. It doesn't do an exhaustive search, so it's really efficient in the way it does, but with some caveats which we'll soon see. Okay, so a few months back, I joined this team at Red Hat, which built this particular platform called OpenShift.io. It's an entirely cloud-based platform targeted for developers to plan, build, test, and deploy applications on cloud. So you don't need, you just need a browser and an internet connection. You can get connected, you can plan your activities for that sprint, you can write code, test it, and you can deploy it as an API on containers. So everything is provided for free, right? So that's the application that's the product. It's a self-hosted solution that's running. Specifically, these are the problems that I started working on when I joined Red Hat, is to make recommendations for developers. So there's two kinds of recommendations that a developer would require. One is on the package itself. So I want to run machine learning using Python. Okay, so what kind of options do I have? I want to run market basket analysis in Python. What options do I have? Or I want to do string matching in R. What options do I have? So that's an option which tells for packages. The other thing is with stack. So you've completed a particular project, and you want the tool to analyze how good your stack is, the list of packages that you use to accomplish a particular task. So this would run through the manifest file, and it would make recommendations on, okay, you can change this because of maybe license conflict, because of there's a better package to do it, because it's no longer used. So there's a bunch of recommendations that you can build on top of it. So that's all stack level recommendations. So if you want to, these were the problems we want to work on. The first thing you want to do is to get data. In this case, data is not hard to get because any of the packages fairly standard practices. For Java, you would maintain something called a pom.xml, which would list all the requirements for that project. For Node, it's packages.json. If you use Python, it's requirements.txt. It will have the package and the versions associated with it. And you could go to the host, the source code repositories, Maven or PyPy, to get the list of all packages that's out there. So the data part is solved. So you get the data from GitHub and other public repositories, load it into our data engineering pipeline, and have it ready to build a model. So we got a Spark EMR cluster on AWS, and everything that we do is mostly done on AWS. We got a Spark EMR instance. We have Elastic Cloud Compute. Data is on S3. Looks like really cool. Just run the FP growth, and we should be done, right? That's what we thought when we started, but we realized that developers are crazy, right? So it's, we saw packages, we saw projects which had more than 1,000 packages. So you take like really large platform-based architectures, marketplaces, they use so many different packages. It's fairly typical to see a small package might have a few components, but the moment you come to a big project, it's fairly common to see a large number of dependencies associated to install that particular project. When you have something like that, which is what we categorize as wide transactions, so each user, one project, has so many items in that particular transaction. So it's really wide. So you have large data, so which is scalability in terms of number of rows, but it's also scalability in terms of number of packages that makes up the particular component. And unfortunately, we ran into a lot of issues. So it's well documented that FP growth runs into memory issues because it keeps track of all sub-FP trees that it generates. So when you work on a big scale like this, it ran into memory issues, and optimizing what kind of machine you want to run itself takes a while. But once that's figured out, even the time it takes to train, because of the huge sparsity of the data, it was fairly common to take like 12 to 14 hours at the minimum to get a model out. You might think that, oh, that's not really long, but when we start building it as a self-serve platform, something which is out there where you can onboard your entire team or your organization into the platform and get started building solutions, the time it takes to get started in providing recommendations is also important, as well as the accuracy, right? So it's a double-edged sword. You can't really wait. You can't tell, oh, we get started, come back after a couple of days, and you can start development. That doesn't really get us the project. So one common way, a similar way which we could use is matrix factorization, which is extremely fast. This is what a lot of collaborative filtering techniques do. A very standard technique is alternating least square, which are extremely fast, where we take a particular user, user item rating matrix on the left, and we want to come up with a tall and wide matrix, a dense representation of that, which minimizes the error of the ratings. So once you have that, it's easy to fill the remaining empty spaces, and you can have recommendations for various users. So this is a fairly well known and well proven methodology, and it works extremely fast. But there's a catch, right? I mean, it gives me the recommendation of the next product. It doesn't generate frequent patterns to it. Just taking a step back, why do we need frequent patterns for developers? Because once I'm going to assign a developer joining my team to, okay, he's going to build a search engine. So we want the recommendations in search already out there so that they can get started working on it as fast as possible. So this is the process that we took to generate frequent patterns using ALS. The first step was to take the input data, which was really wide, and run the ALS model on Spark. It was extremely fast. It has enough knobs to tell how much accuracy that you want to gain, but it was really fast. In a separate process, we started generating a random seed of candidate sets. So the exhaustive generation of candidate set is an expensive process, so we just want to work on a small set, an initial seed that would get started on, and use that as the initial frequent pattern. So this a simple way to think about is all packages, list of all single packages is one frequent pattern, and all two-way combinations is another frequent pattern. So you have something like that. And call the API to find recommend user. We talked about user similarity. So we can use the ALS model to find, for this package, which is the user that would you recommend? So that would give a recommendation on the user who's most similar to that. When you have one package, two packages, it's not going to be, you're going to get a huge number of recommendations, but as you keep adding more packages, it's going to get better and better. Once you know what user that you're going to recommend, the next thing is for that user, what is the product that is going to be recommended. So you have, say, you have 5 products in your basket, you go recommend user who's most similar to that, and then use that to recommend the product. So that makes from 5 to 6. And you add it to the frequent pattern list, and you keep generating it. This entire process brought down the training time to less than 30 minutes. It was extremely fast. And we also added a huge number of knobs, which tells what kind of accuracy that you want, to see that if that's fine. Because when you recommend a user and recommend a product, you can also get confidence scores. And you want to tell, okay, I want to take users only if it's above a particular threshold. So these are things that you could work on. Once this is done, this is how we deployed it in production. So we have the user who comes. It's entirely, this is where the recommendation engine sits on. It takes a whole lot of data from Amazon. A huge number of use cases sit on top of this. And with Spark EMR, we train the model in an offline process. And the model gets loaded and is exposed as a microservice. So we have an API for it. And the entire frequent patterns are served in an Elasticsearch layer. The advantage of, so I talked about retrieval at the start, right? So this helps us provide a very fast search capability within the frequent patterns. So you could do interesting queries on top of it and provide enough knobs so that you can add additional. So this could serve as the basis as we start adding more different kinds of what we talk about, content-based recommendations in addition to this. So that it could really help us do that, and it also helps us bootstrap. So one thing that we announced earlier this month, but will launch very soon, is that you can really get containers of a particular intent, what we call. So if you want to build an e-commerce site, it would generate your entire manifest file and the entire boilerplate code, so we can identify intent and make recommendations. So this would help you do that. This entire platform is free. You could try out. Want to give a thought on why didn't we use deep learning for this, and why did we use more traditional approaches? Is that I want to have a talk idea for next year. So. That's, so there were challenges that we hit with deep learning in terms of cost. It was costing us, and amount of data that we need to get the kind of accuracy that we were seeing in the existing approach. But we are doing this as we start doing more content-based stuff. More and more of it will be deep learning, but at least in the near future, it's going to be a mix of these two models. The frequent patterns are still going to be in the methodology I just talked about, while we'll have more content-based stuff that would be using deep learning. The entire code will be open sourced, I think maybe in a month or two. And these are my coordinates. You can reach out to me on Twitter or my colleague's email. We'd be happy to answer any questions you have. Yeah? Thanks. Yes.